Okay, hi everyone. My name is Karim. I work in program analysis and I lead the programming language group, Maple. And today I would like to talk to you about scalable and precise security vulnerability detection. So, software bugs. We all know that software bugs are everywhere in our programs. So, the thing about software bugs is that the earlier you detect them in the software development lifecycle, the better. So, I'll just show you a diagram here, and this data is from the report by System Sciences Institute at IBM. I think it was back in 2003 or so, where if a bug costs $1 to fix in the design phase, it will cost about $6.50 to fix in the implementation phase, $15 to fix in the testing phase. Can you guess how much it would take to fix this in the maintenance phase, meaning after production, after producing your code? Except somebody said 100 there, right? Yeah. Yes, you're right. It will cost $100. So if you don't believe IBM, you should probably believe Samsung. Remember the Galaxy Note 7 fiasco thing back in 2011 or 13? And that cost them about $17 billion just to recall all the devices that were affected by that software bug that caused the battery to explode while people are using it.
Why was it a software bug? Why was it not a battery bug?
It was a software bug that didn't really get precise measurements from the battery and kept pushing electricity to the battery even though the software didn't get precise measurements there. So it was a software bug actually that caused this.
I did not know that.
Yes.
Is that a lot of money for Samsung?
Well, it wasn't just money, right? Because there was a ban. There was a ban on all airplanes, for example. You can't fly with a Samsung phone. So imagine like how the image of the company was affected by that. And I mean, there is lots more of these recalls. There's the Toyota recall because of the automatic the ABS braking system in the cars that cost them about $9 billion. And there's lots of these. So this is just one example of how software bugs would be costly if you don't catch those bugs early on in the development lifecycle and wait until you catch them later on in the software product lifecycle. A particularly nasty part of software bugs are ones that are related to security. So security vulnerabilities in your application or in your code. An example about that is Java, for example. So back in, was it 2012 or so, Oracle issued a patch for Java 7 because there was a security vulnerability. But it's a cat and a mouse game. So a couple of days after that, new vulnerabilities were found in that patch that they just issued. And they fixed the patch. Then more vulnerabilities were covered a couple of days after that. Then they fixed the patch. Then more vulnerabilities are covered. Then they fixed the patch, and so on and so forth. So it's not just that you need to detect those after production, but testing sometimes doesn't even cover those security vulnerabilities and those bugs in your program. So you need to do something before even you do testing. And testing alone is not enough to catch some classes of these bugs. So a major part or a large portion of these cyber attacks or security vulnerabilities in applications, according to the Department of Homeland Security in the US, 90% of those attacks are due to vulnerabilities in the application layer or the application of the software itself. Basically, software bugs or security vulnerabilities in your code, rather than like phishing attacks or social engineering or other sorts of attacks that can enable those cyber attacks. So 90% of those cyber attacks are due to bugs that developers have in their code and in the program that we can do something about. And if you don't believe the Department of Homeland Security, or you don't believe me or any of the previous slides that I just showed, I want you to walk through this piece of code here. If you are taking the program analysis course, please don't say anything. Just wait until the end. So this is a piece of C++ code that has a vulnerability or a bug in it. And I'll just give you a minute to look at it and tell me where that bug is. Yes. Have you seen this code before?
No, I haven't.
Okay, all right, go ahead.
There's two go-to statements.
There's two go-to statements here, right? Both of them go-to failed. So this is a duplicate. There was an error by some developer that just copy-pasted if statements and they just forgot a dangling go-to fail here. And because they used the same indentation, like visually you can't tell that this is a duplicate. What that does is it bypasses basically that row verified, which verifies the authenticity of SSL certificates in your code, and you can basically bypass that whole thing with that go to fail and exit from the method, even though that you have a valid SSL certificate. So if you think that this is a trivial thing or it wasn't really in a major code base, this was actually in Apple's code base for iOS devices. So if you have an iPhone or an iPad, prior to 2014, you had this bug in your code, in your program, and your devices that you had. And it stayed like that for about 2 years before they actually discovered it in their code base and fixed it afterwards. And for that stupid bug, Apple won the Pony Awards, which is an award that no company would like to get at any given year, that is given to something that is a stupid security vulnerability that should have been easily detected into within their software development lifecycle, but wasn't, and caused a lot of problems for them. Another security vulnerability that many of us probably heard about before is Heartbleed. So what is Heartbleed? So I'm just using here some visualization from XKCD that just explains what that attack looks like. So let's say Alice here is talking to a server, and she's asking the server, give me, are you still there? She's pinging the server, are you still there? And if you're there, please respond with the key phrase, potato. And potato is 6 letters, right? So the server will receive the message, and will check, Meg wants the answer to be potato, which is 6 letters. Great, send that back to her. So the server will send back potato to Alice. Nothing is wrong there. Then Alice would just send another request, and then, hey, server, are you still there? This time, send me the reply or the response bird, which is 4 letters. So the server will see that, and then will respond with bird. And then Alice sort of thinks that there is a pattern to what she's saying, but the server always responds with the number of characters that it asks for. So next time, she's going to try something different. She will say, server, are you still there? And if you're there, I would like you to respond back with the response hat, but I'm giving you 500 letters instead. I'm telling you that the response is 500 letters, even though the key phrase itself is 3 letters only. And the bug was that the server would happily respond back with hat, but with everything else after hat in its memory that include up to the 500 character limit. So it doesn't actually look at the limitation of the string that Alice is looking for, but rather the length or how many characters Alice claimed that the response is of that size. So for example, if you have some public key information that is stored in memory, but is dangling there for whatever reason from a prior process, it would just be sent back to Alice happily, no problem at all. And that was a huge bug in OpenSSL back in 2014 as well, the same year. So the common thing among all these problems is that testing alone is not enough to detect them. As you see here, for example, from the problem with Samsung Galaxy Note and the go-to-fail problem with Apple, Heartbleed was also detected after production, of course, after OpenSSL was around for a few years, and it was discovered only through fuzzing techniques. But the common thing amongst all of them is that they could have been easily detected and even fixed in many cases using static analysis. So what is static analysis? So static analysis is a technique of understanding what is the possible runtime behavior of a program without having necessarily to execute the program. So you're given a program, you have a property that you want to check for, let's call that property phi, and you want to ask the following question. Does this property phi hold before a given statement in the program or not? And then the analysis has some oracle that checks the code of the program, checks some parameters of the program, and then be able to respond to that question with a yes or a no. That's what static analysis is about. Okay, so is that something useful? Yes, it's actually quite useful. It's used in various compiler optimizations like constant propagation, inlining of methods in your program to get better performance, dead code elimination. You will see that used quite a lot in things like Android applications, so that your application has a reduced size for resource-limited devices. Parallelization, so if you have some piece of code that runs on a single thread or a single core, you can actually use program analysis so that you can parallelize the code to run on multi-core architecture. Static analysis is used quite a lot also in developer support environments, so to build things like code recommender systems, code refactoring tools, if you want to extract a piece of code in your program into a method so that you can call it in multiple different places. There is a static analysis running in the background that enables that kind of refactoring in your program to happen. Code navigation, if anybody here has used Eclipse or Visual Studio or IntelliJ, whenever you hit Control space or Command space, depending on your machine, there is a list of methods that shows up there. That's actually some static analysis that reasons about what would be the possible method that you can call at that point in your program, given the context of the code that you are currently developing. It's also used in program verification to make sure that certain devices or certain machines or certain systems like cars, airplanes, space shuttles, or MRI machines at hospitals adhere to certain standards, because you don't really have the luxury to try out MRI machines on patients a few times before you can actually use them in production. So program verification is a form of program analysis or static analysis that can enable this kind of verification. And of course, today's topic, it's used quite a lot in security. So tools like Coverity by Synopsys, Absent in Germany, Find Bugs, Check Marks, FlowDroid, all these tools are different tools that try to check, does your application or your code base, does it have any security vulnerability or data leaks in it or not? And it's used quite a lot there. So it seems that static analysis is a very useful method or technique to use. But that's not really the case in practice. Otherwise, all these companies wouldn't have suffered from all these issues like Samsung or Apple or Toyota or Medtronic or any of these companies. So why is that the case? What is the problem that's causing static analysis not to be used as often as it should be in practice? The way I see it, there are three problems. One is the scalability of the analysis. Can you analyze large code bases like Google's code base, which is, I think, 84 terabytes of data or something? And whenever you join Google, you actually have access to that whole code base, where you can check out, well, you can theoretically check it out all at once if you want, but you probably don't want to do that. Precision of the analysis. Do you have an analysis that just generates thousands of issues to developers and warnings that don't really make sense or are not really relevant to developers? And that makes your analysis doesn't scale to that large code base and just keeps generating lots of false positives. And the usability of your tool. Do you have a tool that has a user interface that appeals to developers and doesn't disrupt their workflow or not? So in today's talk, I'm just going to focus on the scalability and the precision aspect of them with respect or in the context of security vulnerabilities and detecting security vulnerabilities in your code. Okay, so some of the security-related static analyses that are typically used to detect vulnerabilities in your code. What are some examples there? One example, I'll just use this code example here to showcase some of these examples here, some analysis examples. So this is just the main method, has some arguments, and you assign the value null to an object x, then you assign x to y, and then you call y to toString. So in this case, you will get a null pointer exception because y here actually is a null value. It doesn't hold an actual object or an actual reference that you can dereference to call toString on. So to detect that kind of null pointer exception, you would have something called a null pointer analysis or a nullness analysis that can enable you to know to track down the data flow from x to y to that point here that says you could have a null pointer exception at that point. Beware, you should fix your code. Another example here, if you have, and I think the Nielsen will like this one, so you have an SQL query here that selects a bunch of stuff from user ID equals some data, right? And that data happens to be y. Y is, you take that value from x, and x happens to be one of the arguments that you pass to the method. The problem with that is that y here is not sanitized. So you can basically have an SQL injection that manipulates the schema of your database and changes what the behavior of the database should look like. If you don't have this y sanitized, or if you don't check for the value of y, whether it has illegal characters or illegal things like dropping the table and just making, like you can have y basically here be where user ID equals, I don't know, something or true. So it will always evaluate to true, right? And then you can drop the table afterwards. So there is an analysis that can allow you to detect those kind of opportunities in your program where you can have such privacy leaks or SQL injections. And this analysis is called taint analysis. So it tracks basically sources of information or private information in your code. In this case, this would be the y value here, because this is the problematic value that can cause this problem. And then figures out, okay, this could flow from that part of the program or that location in your program. And you should be aware that this could be a problematic issue in your code base. The last example here is, again, you're creating some file, x. You're passing around that file somewhere in your program. And then at the end, you're calling y.close. And the question now is, did I properly close all the file descriptors that I have in my code or not? Because otherwise, imagine doing this in a loop, maybe in different parallel threads, and you can just deplete all the resources in your code, and you don't know why you can't access the file system anymore. So you have a sort of a denial of service kind of thing. You're denying all the processes in your program to access the disk. So there is an analysis that can help you detect that kind of issue in your program, and that analysis is called type state analysis. So a type state analysis just tracks the states of your different objects that are available in your code and checks that they conform to a certain finite state machine that tell you that to open a file, you need to have to create it first, then you can open it, then you can close it. So we have seen 3 different types of analyses that can help you to detect security vulnerabilities in your code base. So all these analyses, one way or the other, underneath the hood, or under the hood, they are doing, oh, by the way, if you have any questions, just interrupt me in the middle. Don't wait until the end. So all these types of analyses, what they are doing under the hood is that they are doing some tracking of some data in your program. They are checking where that data comes from, where the data flows to, what are the different statements in your program that affect the flow of the data, and where the data flow stops in your program. But what you really want to do is you want to have a precise static data flow analysis. You don't just want to have any kind of data flow analysis, you want to have precise information. Otherwise, you will go through the road of having lots of false positives, and then the developers are not going to use it, and then you're going to have all the issues and the errors that I talked about in the beginning of my talk today. So what is particularly interesting or difficult or challenging about precise static data flow analysis that makes static analysis in practice such a big deal? So let's have this code example here. So in this code example, I have a main method, and that main method, I'm creating a new file. I'm assigning that file descriptor to the field z or z in the current class, and then I'm calling foo, and then I'm closing the file descriptor, and then I'm calling foo again. And then I have 2 methods foo here. One, where I have where it receives a parameter y, and I'm calling y.write, so I'm writing some data into the file. And the other foo, I'm using the file descriptor from the field of the class, this .z, to write that data that I have. So to reason about things like method calls in your program, and in this case, this is the foo_x calls there, and the y.write call here, to be able to do that, you need to differentiate between these 2 method calls here. Because the context or the surrounding environment around each call, or each call site in this case, is different. So the result of the analysis when you call foo on that line here may be different when you call foo on that line, specifically because of the x.clause in between. So to be able to have such a precise data flow in your program, you need what we call a context-sensitive analysis. An analysis that can differentiate between different calls to the same method from different locations in the program, given different inputs. So that's what I call context-sensitive analysis. Okay, so one parameter that we need to take care of. What else is out there? Well, I have these field writes here, and field references to fields. So here I'm writing some value to this with z, and here I'm using that value to call write. So one thing I also need to reason about right now is, what is the data that flows from one field to the other? How am I accessing those fields? Is that a legal access or is that an illegal access? Does Z point to some object that actually exists in memory, or does it point to a null reference? How do I know that? And for that, I need another property for precise static data flow analysis, which is field sensitivity, being able to differentiate between accesses to different fields, to different objects in different paths in my program. So now we have these 2 properties. They have to be there in the analysis for the analysis to be a precise static data flow analysis. Okay, so now the analysis has to be both context sensitive and field sensitive. In the literature so far, up to like last year, what this type of analysis has been described as is using a pushdown automata that just represents the accesses or your variables in your program. And that pushdown automaton has 2 stacks. One stack represents the method calls in your program. So you call main, then you call foo, you call bar, you call foo again. So this just represents the sequence of calls that you have in your code. Right? So that's the first stack that we have. The other stack that we have is a stack of field accesses. So you access field F, then you have another dereference like f.h.g.f, for example. So you have a stack of field accesses, you have a stack of method calls. And the automaton has to keep track of both stacks simultaneously to be able to have a context-sensitive and a field-sensitive analysis. So far, so good? Not really, because this is actually an undecidable problem. Like everything we have in program analysis in general is a very tricky field because everything that you want to do is an undecidable problem because it reduces to the halting problem. So if we can solve it, we can solve the halting problem. I wish, but we can't. So this is also an undecidable problem, having context-sensitive and field-sensitive at the same time. So what do people do actually? Here's what people do. They get rid of the stack of fields. We don't care about that anymore. But we still need to track how I'm going to access fields in my program. Otherwise, I don't have field sensitivity. So they replace that with something else. They expand the automaton that they have in the pushdown that represents those variables and encode the accesses of the fields in there in something that we call access path. So how you are accessing the fields in your program. Or sometimes there is another approximation for it called access graphs. So think of it as a finite state machine of all the different accesses to fields in your code. So that way you only have one stack in your pushdown automaton that enables you to have a decidable problem now, while still representing those field accesses in your code. The caveat here is, now that we don't have this stack of field accesses, I have to limit them somehow. So I have to say, I'm not going to represent all field accesses f.g.a.b.c.d and so on. I'm just going to give a limit, let's say 3. So for me, as an analysis, f.a.b is the same as f.a.c. So I'm just going to name them f.a.star, right? Just to have an over-approximation of that. And that's what k-limiting here means. So that's again another problem. Why is it a problem? Because having this k-limiting or k-limit yields again too many false positives because you are over-approximating over different field accesses. Yes, they are to the same object, but they are different fields. So you might have on one field axis that your program has a security vulnerability, but from the other field axis, it's safe. And now you are combining both together and you're saying whether it's this or that, you're going to get a security vulnerability. So that yields too many false positives in the analysis. And not only that, it actually makes the analysis run slower because you have bigger data sets and bigger access graphs and access paths to reason about. So it slows down the analysis, it makes it less precise, both at the same time. So to remedy all these two main issues, what we worked on, my PhD student Johannes Speit worked on primarily, is something called synchronized pushdown system that overcomes these two main problems. So what is that? We still want to have both context-sensitive and field-sensitive analysis. But what we thought about is, what if we separate them together, separate them from each other? So let's say I want to have the context sensitivity alone and field sensitivity alone. And one nice property about having this separation or this conjunction here is that this is an over-approximation of that. So what that means is, if I do this over-approximation, I'm still guaranteed that I have a safe over-approximation. So I'm not going to miss anything that this analysis is interested in. So we're good. I'm not going to miss any security vulnerability in my code if I separate these sensitivities from each other. So what does it mean to separate these sensitivities from each other, given that setup of the pushdown automaton? So here's what I'm going to do. I'm going to have a pushdown system or a pushdown automaton for the calls. It's separate. It reasons about variables separately. It still maintains its own stack of calls, so we're good. I can follow what the sequence of method calls that I have in my program look like, and which methods I have in my program. So that's great. So now I'm context sensitive. And then I'm going to have a separate pushdown system, a separate pushdown automaton that represents the field accesses in my program. So the difference is that now I have two pushdown systems as opposed to the other system or the other undecidable problem where you have one pushdown system that has two stacks. Now I have two pushdown systems. Each one of them has its own stack that represents, one represents the calls, the other one represents the fields. So far so good? Okay. This problem is decidable. So yay, it's great. It's not undecidable anymore because I have one stack, I have one pushdown automata, and that same paper that proved that the context-sensitive and field-sensitive that has one pushdown automata with two stacks is undecidable also showed that this here is decidable. And this is what people have been usually doing. And the difference compared to the state-of-the-art is that instead of having access paths or access graphs, we have this pushdown automaton to represent the field accesses in my code. The nice thing about this also is that we no longer have k-limiting. I'm no longer assuming that A root B root C is the same as A root B root D. So I avoid any loss in precision, which also yields more scalability to the analysis compared to the state-of-the-art. So let me walk you through a couple of examples of how does actually this look like. What does that SPDS or synchronized pushdown system look like? So this is a piece of code. It's very simple, only 10 lines of code. You have a main method. You're creating an object of type C, let's call it O1. Then you are assigning it to S, you're calling foo, and the method foo has some condition that tests some value, and based on that value will return foo T, and then at the end it will return T. So there is a recursive call here as well, just to make our life more miserable. Okay, so let's first track or trace through the automaton of calls, so the pushdown system of calls. So here we have the object O1, and if I have this doubly lined state, that means it's an accepting state of the pushdown automaton. So you can end at this state. That's what I mean by accepting state. And the edges here represent the transitions from one state to the other, and the labels on the edges tell you how you're going to transition from one state to the other. So here on line 2, because I'm creating that object, now I will start tracking the variable r in my code. And I know, so the way you read this is that r can point to the object O1 because of the line number 2, right? This is how you would interpret this kind of drawing here. Then on line 3, because I have the assignment statement, that means that, well, on line 3, r still points to O1, right? Nothing has changed. But now also s points to O1 through the assignment statement on line 3. And this graph here is basically just represents the fact that S is now reachable in this automaton because of that transition from R to S. All right? Then we have a method call, and this is where the fun begins. So now, remember, we're doing the automaton of calls. So I'm tracking those calls in my program. So we have push rules in the pushdown system. Whenever you have a call, you have a push rule that determines what the call flow is. And in this case, I'm calling the method foo, passing it S to T. So now T becomes reachable in the pushdown automata. And then we go to the method foo. And because we have a recursive call, so T can call itself as many times as possible in the pushdown automata. And eventually, it will go to O1 because of that assignment statement at 4 because of the method call. Right? Any questions so far? All right. And then the return at the end would just return U to the call site of the method foo, and that will happen on line 4. Any return that you have in your program would be represented by a pop rule. So you're popping something off the pushdown system, and you're popping it with that epsilon that represents popping rules in your code. So now we have seen what the automaton of calls looks like, or the pushdown system for calls looks like. So what are the advantages there? Advantages are, we have an analysis that is flow sensitive, which means that the analysis tracks the instructions in sequence in your code. So the order of the instructions matters. It's context sensitive because we have a trace of the calls in the program. However, it's field insensitive because it doesn't track any field accesses. So we lose that. But we'll see how we remedy that later on. Now let's see the automaton of fields, the other pushdown system. So I slightly changed the code just to have a field access here. And we're going to do exactly the same thing. We're going to track the field accesses this time instead of method calls in the program, and we're going to update the automaton and also the reachability graph that we have accordingly. So in the first case here, we're creating an object and assigning it to S. So S can point to 01. And then because of that assignment, store to r.a, we have a push rule that represents the field stores, and this is how it is represented in the pushdown automata.
Are your transitions here different? The labels where they transition, now they're not.
Yes, so the labels now for these transitions, thanks for pointing that out. So the labels now, because I'm tracking fields, they are what is the field access that would get you to that state in the pushdown automata. In the previous one, for the pushdown for calls, it was the line number that has the call side that allows you to go to that call in your program. But again, epsilon here just means it's a pop rule, meaning you're reading a field. And if you have a letter or if you have a field, that means that you would access, so here, so r.a would reach that object 01. And like I said, like pop rules represent field loads. And that's why you have all these epsilons here, just to state in the pushdown automata that those epsilons represent pop rules or reading from fields in your program. So you can now have reading fields and writing to fields in your program. Okay, great. So now we have another pushdown system for fields that is flow sensitive as well, because it tracks the sequence of instructions in the program. It's context insensitive, because as you see from the pushdown automata, there is nothing that says anything about calls in the program. It's only field accesses. So this would be a field sensitive analysis. So now we have a pushdown system of calls that is context sensitive but field insensitive. We have a pushdown system of fields that is context insensitive but field sensitive. Now what do we do with them? What do you think we would do? Sorry, somebody?
And together.
And them together, right? So we have two things, but I want to merge these two things here together. So we're going to and them together in a way, but it's not really an intersection or an and. It's really synchronizing or having an accepting state where you find that state in both pushdown systems. So if you have a state that is acceptable by both pushdown systems, then it's going to be an accepting state in the synchronized pushdown system. So we split apart the problem into two different pushdown automata, one that handles calls, one that handles fields, and then you sort of intersect both pushdown automata later on. Yes, it's an over-approximation, but it's a safe over-approximation that enables us to have this kind of flow sensitivity, context sensitivity, and field sensitivity in the program, in the analysis itself. So now we have all three of them, which is great. So SPDS is great. SPDS rules. You might think, okay, does that actually work? How does it fare to the state of the art there? So we ran a whole bunch of experiments. I'm just going to show you one here. So on the x-axis, I'm showing the number of field accesses that you have in the program. So if you have f.a, this will be 2, f.a.b, this will be 3, and so on and so forth. And on the y-axis, I'm showing the analysis time per object that you're tracking in your program, right? And that number is in seconds here. And I'm going to show 5 different configurations of analyses. I'm going to show you 4 configurations for k-limited analyses, so that was the state of the art before our work, for k equals 1, 2, 3, 4, and then compare to SPDS. So k equals 4, you pretty much have no chance whatsoever. Like it really increases exponentially given the number of field accesses. K equals 3, still exponential, a little bit better. K equals 2, also still exponential. So as long as at the moment that you hit k equals 2, so only 2 field accesses in your program, the bar goes up really high. K equals 1 is heaven. It's great. We all want to be there. F.A.B takes the same amount of time to reason about like F. So where does SPDS fall in this evaluation here? It's actually right there. So in other words, we have a performance that is very, very close to k equals 1, but we have the precision of that is equivalent to k equals infinity, because we don't have any limit whatsoever on the length of the access path that you are representing in the program. Yes?
It's not clear to me what you are calling number of field access in your X.
It's the length K in K limiting.
Dot.
Yes. So the number of field accesses means, let's say you have f.a.b.c.
I know. But that would be for a single access, right?
So that's the maximum one, in the largest one that you have in your
That's what I'm
program.
trying to figure out, because if you have a program,
Yeah.
you can have many such instances. Some will be just f.a, some will be f.b.
Yes. So I'm talking about the largest one in your program.
But does that determine the time?
That determines the time, yes. Because it's
enough for me to have one that's 18 for me to go to that time, or the frequency in which I have in the program.
The frequency doesn't matter, because if you have a field in your program that is of length 18, you need to configure the analysis to handle that case. And you cannot configure the analysis independently for each field access separately. It's a blanket configuration for all field accesses.
So the number of field access that you're showing here is the configuration
of the analysis, yes, which it should be enough to handle that case in your code or in your program. I'm glad that you asked this question, because do we actually get to see like lengths of 14, 15, 18, and these kind of things? And the answer is yes. In the Eclipse IDE, there's a field access that is 13 in length. So that sequence here has 13 field accesses. And if you don't have that kind of level of precision, you're not going to capture the behavior of that field whatsoever. So yes, it shows up in practice. Okay, that's great. So on paper, things look really, really well, right? But does it actually... Is that thing, SPDS, really practical? Can we use it for something useful? Maybe you can find a field access of that length, but yeah, who cares? Like, it doesn't really affect the security vulnerability in my code whatsoever, so I don't really care about it. So I'm just going to show you some anecdotes there. It is actually very useful. I'll show you a few things. So one study that we did after that was we took all the 2.7 million artifacts from Maven. We ran a security analysis tool that we have that uses that SPDS infrastructure, and we found that 68% of the Maven artifacts that use the Java cryptography API are vulnerable. They have some insecure use of that API in them, one way or the other. Almost 70% of those artifacts. This is a huge number, by the way. If you think 70% is not that big, this is a huge number. And yeah. One other interesting result that we got is that, and now I can disclose this, that same tool that we used that uses SPDS, we were able to find security vulnerabilities in random Android applications that we got from the Google Play Store, and one of them was the Semantic Identity Safe product. So that is some product by Semantic, the company that sells the antivirus tools, and that is supposed to be a password manager, a safe password manager. But they had an error or a security vulnerability in their cryptography in the code that we were able to detect using our code. And we worked with them for a few months before they fixed the error, and it was actually marked as a medium bug, so it was higher on their scale. And now you can actually get more information about that CVE now that it's fixed and it's publicly disclosed. And that was thanks to that level of precision that we were able to get from the SPDS system. Another bug that we have is a bug that I can't actually disclose because it's not fixed yet. It's from a major bank in Germany that still has some problems with their password management code in their application. Hopefully I can disclose this soon once they fix the bug in their code. But we were able to detect this in multiple different applications from different industry-grade products out there. Another thing, so the tool that I was talking about is CogniCrypt that uses SPDS as an infrastructure. And that tool now is actually an Eclipse Foundation project that many people are contributing to. And this is just an example of how this looks like in your IDE. So if you have an Eclipse IDE, you can use CogniCrypt, and Kristen right there is working on that CogniCrypt thing as well to extend it right now. And this is just an example that shows you how this can be used. So imagine you're a developer, you're writing some code, here's the IDE that shows the methods, and you're using algorithm, which is an AES algorithm, and you'll see right there in the gutter there is a marker that tells you there is an error there in your code. And the error is that you shouldn't be using AES plain, you should specify the blocking mode that you should use with AES. Otherwise, it's insecure, it's a security vulnerability in your application. So this happens in real time. So while you are writing your code, it's detecting what you are doing and detecting any security vulnerability in your application. And we couldn't get that level of performance without having the synchronized pushdown system automata that we worked on. So now this project is, like I said, it's an Eclipse Foundation project. It's open source. People can contribute to it. And you'll actually, if you go to that link, you will see the logo of the University of Alberta there, because both myself and Sarah and Adi are working on that project. We started it actually when we were there in Germany. So the university is recognized as one of the international institutions working on that project there, which is nice. One other thing that was nice is that we got a Distinguished Paper Award at POPL, which is the prime or flagship conference in programming languages. That was back actually in January 2019. And that was Johannes while he was presenting the paper. So the academic community also appreciates the level of detail that we had in the paper, the level of theory and the solid foundation that we build this infrastructure on, not just from the practical point of view, but from the theoretical point of view as well. The other nice thing is that Johannes defended his thesis a couple of days after we knew that we got a Distinguished Paper Award, and a day before he presented the paper at POPL. So now he's Dr. Schweit, so you can get actually a PhD out of this line of work if you're interested. And if you are, please talk to me after the talk. Okay, that's it. Quick recap of what I talked about today. Static analysis is good. It can help you detect different security vulnerabilities in your application. However, precise static data flow analysis is challenging. It's an undecidable problem in general. And in the cases, the state-of-the-art prior to SPDS, you had to use some limitations there that make the analysis really, really imprecise, that yields a lot of false positives. And I showed you today the synchronized pushdown systems that we worked on in the last couple of years that enables both high level of precision and also high level of scalability. And I walked you through a few examples of how this could actually be used in practice, how this is practical, and how this was appreciated by both people from industry and people from academia. That's it. Thank you. And I'm open to any questions.